All right, so we're going to pick up where we left off with rational functions. Our next topic is to graph these rational functions without a calculator. Now, as you're out of the classroom working on this concept, make sure you have the discipline to not use your calculator. That with this lesson, with the exit ticket, with your homework, that way you'll be prepared when we return to be able to perform this on the test. All right, now, honestly, the good news here is that you're ready for this concept. In fact, really everything that we've done so far with thinking about the numerator and denominator and all these rules, they still work. The only new idea here is to be able to draw the graph. As you will see, when we draw this graph, it's just going to naturally flow with what we've already been discovering with the calculator. So we're going to take this example here, 3x divided by x minus 5, and let's analyze it. As we begin to do that, you want to start, as you always have, with the vertical asymptote. That's definitely going to be at 5. You don't have a hole in the graph on this problem, so we can move on to the horizontal asymptote. Here you should notice that the degrees are both equal. They're both 1. So we're going to use the A over B concept, which will give us 3 over 1. Of course, that's your horizontal asymptote. Now, the y-intercept is when you plug a 0 into the equation. Again, just as we've done before, you plug a 0 in, you get 0 over negative 5. Of course, that comes out to be 0, otherwise known as the point 0, 0. And then your x-intercept is when the numerator is equal to 0. It's really when the whole equation is equal to 0, but in this case, the numerator is going to equal 0 when x equals 0, which again is the same point, 0, 0. All right, so we start putting these features on the graph, just like before. We can be confident with with labeling and drawing that vertical asymptote, the horizontal asymptote, and our intercept, which both of them, x and y being at 0, 0. So when you think about drawing this graph, remember that every graph you've seen so far has always approached the asymptotes and passed through the intercepts. It's not going to be any different now that we don't have our calculator. We're still going to draw the graph to approach the asymptotes and pass through the intercepts. So that means that since we have an intercept at 0, 0, that the graph will definitely have to pass or cross through that intercept. It'll have to connect with it, touch it, and then as it continues, it's very likely that it will go down as it approaches that asymptote and go over here to the left as it approaches that. Now, the reason I say it's very likely is because we should also consider simple x and y value input-output of our equation so we know exactly what direction this branch is going to go. And so that's why we have this second idea that we will investigate some points. We'll investigate some points that are near the vertical asymptote to determine the exact location, the exact of this graph. So we notice that the vertical asymptote of x equals 5 actually divides this graph into two sides, the side that's to the left of 5 and the side that's to the right. And even though it might not ultimately be necessary for this problem, as you may know that the graph that we drew is correct, I still want to model a simple idea of plugging into this equation and determining the output. And in this case, when I plug in 4, I will very quickly be able to determine that the output comes out to be negative. It comes out to be negative 12, and simply what that means is that the point 4, negative 12 is going to be on this graph, giving us further proof that the graph is going to be going down on the left side of the asymptote. Now, when it comes to drawing the other side of the graph, in other words, the side to the right of the asymptote, we kind of have two possibilities. There's this possibility for a branch over here, sort of at the bottom right side, and there's also a possibility for a branch up here on the top right side. Now, only one of these branches is correct, and it turns out that it can't be this branch that I have drawn here to the bottom right, because that would create another x-intercept. Now, the other reason that we know that it can't be this branch on the bottom right is because of a simple input-output. And as I said before, although it may not be necessary for this problem because we already have pretty good evidence that the graph will be to the top right side, I still want to show you this idea of plugging in an x value and finding the y value. As the problems get a little bit harder, we'll need to use this skill, and it's pretty easy to see here that the y value comes out to be 18. Now what that means that the point 618 is going to be part of this graph, which gives us further proof that the branch would have to be up here in the top right corner so that it can pass through the point 618. So we've successfully drawn a graph that approaches the asymptotes and passes through the intercepts. We've also investigated a couple points that are on each side of the vertical asymptote. That way we would be able to know the exact location and behavior of each of these branches. Now I'd like to add one more idea to our concepts of rationals, just to allow us to think about how infinity, the concept of infinity, can also connect with asymptotes. And simply put, we're going to create a table. I call it the asymptote infinity table, where we just make a statement that describes the two behaviors of this graph. The horizontal asymptote, of course, is y equals 3. What that means is that as the graph goes to infinity, maybe I should say more specifically, as x goes to infinity, that's when we discover that the y value approaches that asymptote of 3. So we make a statement that says as x gets very large, that the y value approaches that asymptote. Now we could be a little bit more specific here. We could say plus or minus infinity because it does happen to both the left and the right. And then we can make a statement about asymptotes of infinity that relates to the vertical asymptote. And in this case, we want to realize that this time it's x that's approaching the asymptote. X is approaching the value of 5, but it's y that is going to plus or minus infinity. And so we just see a simple delineation here between the two types of asymptotes. One of them, the horizontal, is when x approaches infinity, but for the vertical asymptote, it's when y approaches infinity. And I'm going to ask you to always make these little horizontal, or make these asymptote and infinity tables as part of your answer that goes with your rational graph. All right, let's take a look at a rational function that's a little bit harder. Again, we're going to do this without a calculator, so continue to think that way as you're outside of the classroom. You look at a problem like this. As we've said often, if it can be factored, factor it. Clearly, the denominator can be factored, and so can the numerator. So I would suggest that you think of the problem in its factored form. Now notice I took out a GCF of 2 for the numerator. That leaves me with the ability to factor x squared minus 9 to be x plus 3x minus 3. Now you look over your rational function in its factored form, and it's pretty easy to see that there's not going to be a hole in the graph since there's not a common factor. That means that my vertical asymptotes, or that my zeros in the denominator will both be the vertical asymptote. Now, the horizontal asymptote might be easier to go back to the original form of the problem where we have equal degrees. So, again, a nice example of using a over b, in this case 2 over 1. The y-intercept. If it was me, I would also go back to the original form of the equation because you can plug a 0 in and very quickly see that you're going to end up with just negative 18 over negative 4. Negative 18 over negative 4, a little bit of simplifying, work that out to be 9 halves. Of course, the same as 4 and a half. So your y-intercept is at 0, 9 halves. Now your x-intercept, that's when the equation's equal to 0. But when the equation's equal to 0, that's only going to happen when the numerator is equal to 0. Of course, it's in factored form, so it's easy to see that that's going to be plus or minus 3. So we have our features that we can start to put on a graph. All right, so go ahead and get your asymptotes sketched and located. Go ahead and get your x and y intercepts. Get them labeled, and we can start to see how the branches of this graph are going to all come together. Now, it's important you realize that your vertical asymptotes are at plus or minus 2, but your x-intercepts are at plus or minus 3. So locating them in that position is important. Same thing with this y-intercept. The y-intercept's at 9/2. That's the same as 4.5. So that's definitely greater than the horizontal asymptote. It would make sense, of course, to locate them accordingly. Now, we have reason to believe that since the graph is going to pass through the intercepts and approach the asymptotes, that we would have a branch in this kind of bottom left corner and bottom right corner. Now, again, we would say we would have reason to believe. It would also be reasonable to consider plugging in and making sure that this is the direction that the graph goes, particularly when it comes to the middle branch. Okay, now the middle branch, we've seen it do many things over the last week or so. There's been a problem where we've seen the middle branch have a little S-curve. Of course, this creates a dilemma because we end up creating another x-intercept. So it's likely not that. There's also the possibility that this middle branch might be a little S-curve going this way. Again, it's not going to be the case because we make another x-intercept. I'm simply helping you realize that these things can all happen in the middle. There's also the possibility of this. You're allowed to cross a horizontal asymptote, but once again, you create extra x-intercepts, which would not be allowed. So there really is only one possibility left, and it would be this branch that would have to be somewhat of a U shape here in the middle. Now, there is another piece to this no calculator graphing, and that is picking some points and plugging them in. Although you might feel that that's not necessary for this problem, and I would honestly agree it's probably not necessary. It's always something that you can consider. If you pick some numbers that are around the vertical asymptotes, if you were going to do this, you would probably pick like 1 and -1. You could plug them into the equation. Now, it's interesting whether I plug in 1 or -1. I'm going to end up with the same output since we're simply squaring that number. And the output looks like that it's going to come out to be something around -16 and -3. Now, that's a positive number, and a little bit of no calculator math would tell you that it's a positive number that is greater than 5, okay, because you have 15/3, which is equal to 5, but 16/3 would be a little greater than 5. It's a positive number. It's a positive number that gives us affirmation that the graph would have to be up above as it moves in this U shape. And if we wanted to, we could test a point that is in both these bottom corners. Now, again, I'm just trying to give you some things to think about. It really is likely not necessary to do this, but if I wanted to, I could pick a point, maybe like x equals 10 or -10. Now, why am I picking 10 and -10? It's easy to square. We can square plus or minus 10. It's going to come out to be 100, and we're trying to do this math out of calculator, so we end up with 200 minus 18. You're also going to end up with 100 minus 4. So we end up with something in the ballpark of 182 over 96. Now, if we are really trying to do this out of calculator, we'd have to conclude that 182 over 96 is a number that is less than 2. It's less than 2 because of the numerator, of course, and its relationship to 96. So that just gives us another affirmation that the graph is definitely going to be less than 2. It's going to be below that horizontal asymptote, just the same way that we already drew it. So to add the asymptote infinity table just as some extra knowledge, some extra information. It's true for this problem. We can describe the horizontal asymptote. Remember, horizontal asymptotes are always as x approaches infinity. Since we see that it's approaching on both sides, we could say plus or minus infinity. But the most important thing here is that you then conclude that it's y that approaches that horizontal asymptote. And then when we come to the vertical asymptote, it's really the reverse of the statement, because now it's x that is approaching the vertical asymptotes. You could condense this to be plus or minus 2. And notice that the y value is the one that's approaching plus or minus infinity. All right, so last up for today's lesson is an exit ticket. Just like had we been in class, this would be a perfect problem for you to test your knowledge, draw the sketch, and do it all without a calculator. So we're asking you to have that discipline, and what I'd like you to do is just do it in your notes. You're going to take a picture of it, and then you're actually going to submit it using the exit ticket submit form that you'll see in today's from today's Google Classroom post. And I don't want you to worry about particularly what work you might or might not show. Sometimes the work is really just looking at the numbers. But certainly if there is a little work, something that you do to the equation, something you do with plugging in numbers, you should show it. And then make your sketch, labeling as accurately as possible the significant parts, and don't forget to make the little table, the infinity asymptote table. All right, and when you're done, then you want to take a look at page 157, practicing these skills, and I will give you further instruction tomorrow with what we'll do. I'll give you further instruction in the next posting, what we'll do with that homework.